So welcome again to our next session. So today we are going to have the method of sections. We are still on truss analysis. Previously we had the analysis through method of joints, okay, where we had applied equilibrium of concurrent force system, meaning the forces will intersect at a single point. So we have that in our method of joints. We establish the x and y axis label of the forces and then apply the two equilibrium equations. So in this type of analysis, we cannot really rely on summation moments when it comes to analysis of trusses using method of joints. Okay, so by this time we are now applying the principle of non-concurrent force system wherein we can maximize these three equilibrium equations. So it permits us to determine the internal forces in almost any member without proceeding to that member by joint to joint. So we have witnessed, or we had experienced how tedious is the procedure when it is analyzed according to joint analysis, because as we can see there are a lot of joints before you can reach the joint or the member at the center, or you proceed to the edge before you reach a certain member. So that is how tedious the process is. However, nowadays we have a lot of softwares that are capable to analyze a certain structure even in a 3D configuration. So one of the purpose of method of sections actually is for an experienced engineer, he or she knows where is the most critical section of the truss member. That is why it is feasible to use this analysis if he or she intends to investigate or analyze the truss structure. And as we all know, the principle to this one is actually a cutting plane through the whole truss, separating it into two parts. So we are gonna choose what would be the most convenient side, whether it is the right side or the left side. However, there are restrictions in cutting plane, and let me summarize all of the techniques here in applying this method. Number one, as much as we can, we do not want a cut section involving more than three members. So that is why we do not cut a cutting plane, or we do not place a cutting plane in a section where there are more than three members. Because as we all know, we have only three available equilibrium equation in a determinate structure. So these are those equations. Another technique, we take moments at the point of intersection of the members. So this is to eliminate unknowns, because as we all know, the moment involves distances. Now, if the two or more, or two forces will intersect at a certain point, therefore these two forces will have no moment arm. In that way, you can eliminate unknowns. And then the next one, and of course we are gonna choose the most convenient side, whether it is the left portion or the right portion. So it is actually the judgment of the uh, student, or the one who analyzes the trust. So let us have a simple principle or illustration on that. So if we have to consider a certain trust here, so load it as follows, and we are concerned with the members along the midpoint of this truss. Of course, you have to start with the force members, or the joint with only two force members, and then proceed joint to joint before you will reach those joints with these uh, unknowns. So what you do is to make a cut section here considering the left portion. Of course, in that case, you'll be needing the reaction at A. So let us have the section here. So we consider and label all of the forces involved in the left portion. And the cut members are subject as unknown variables, in which just the same we will have an assumption on the direction of these cut members. Now if we are concerned with the force dF, say we are going to label first all of the members here. So dF is here. So we think of a way how to intersect the other two variables. If we are concerned with dF, we try to intersect dg and eg, and eventually they will intersect at a certain point, which is at point G. So don't worry about this, because you might think that point G is not within the truss. That's all right, but what is important here is that you have already intersected the two. So we just take note of the distances here and apply these summation moments at G. We can get the value of dF. If we are concerned now with dg, so dg is actually the inclined member here, and the inclined member here is having a two components, vertical and horizontal component. But the other forces here are only concentrated on horizontal. So there is no vertical component of dF as well as eg. So we will take advantage of that, and then for dg, we'll just apply the equilibrium equation along the vertical axis, because df and eg will eliminated when we use this one. And as for eg, as we can see, the other forces aside from eg is dg and df. So again, we will find a way to intersect df and dg, and then we will take moments at d and equate it to 0 so that we can get the value of eg. So what is important here, wherever that is point, you just consider how long or what is the distance of that point to your forces. So by that, this method of section is demonstrated. So let us now proceed to a particular example. So here is the problem. The truss is loaded with three 1,200 pointed loads along C, E, and G. So the base span is 12 feet for each of the span. We have here an 8 feet height here and a 12 feet height on the king post. We are to determine BD, BE, and CE of this bowstring truss. So the first step, of course, is to determine the reaction. And this is symmetrically loaded, so 1,200 will just be multiplied by the 3 times 3, and then just divide it by 2, because it is only shared by these two reaction forces here. And obviously there will be no horizontal force there. That is RA and that is RH. Each of those will have 1,800 as a reaction. So if you're concerned with BD, BE, and CE, so interestingly, it will fall into one section. Okay, so this cut section will pass through all of these unknowns here. And of course, if we're going to choose between the left and the right portion, it is much convenient to choose the left portion, because there are fewer forces at the left portion. So this is section AA, and then we consider that portion. So here 3 force members will be cut and considered as variables here, namely BD, BE, and CE. So of course, we assume direction for BD. I'm going to assume it as a compression. For BE, say tensile. And for CE, say a tensile for CE. So this composes section AA. Of course, we also need the dimensions here. Here are the dimensions, as well as the slope. So we need to establish the slope of these diagonal forces. So if we investigate the slope of BD, so here it is, we'll just get the vertical and horizontal slope. As we can see, we just established the triangular shape here on BD by making a line here. And this dimension is 12 minus 8 is equal to 4 because this is 8 feet. Note that this dimension is also 12, so we have a slope of 4 and 12. So reducing this into the simplest numerical value, we just divide it by 4, so therefore this is 1 part of 4, and the horizontal will be 3 parts of 4, which is 12. So we have a slope of 1 is to 3. We place it here on the member BD. We also get the slope of BE. We have to establish the slope, and this is 8 and that is 12. Actually, 8 is 2 parts of 4 and 12 is just the same, 3 parts of 4 also. And then we place it here. We have now completed the slope of this diagonal. Why do we need to do that? Because we will be referring to this slope if we are concerned with or resolving these forces into its component. Completing the slopes, especially the hypotenuse, this is 1, 3, and square root of 10, and this 2, 3, and square root of 13. Solving for BD, here is BD. So the pair of BD, or among BD, the other unknowns is BE and CE. So if we are concerned with BD, our next question is, could we intersect BE and CE? Of course, it is obvious that it will intersect at point E. So we note the distance 12 here and then take moments at E. So we have BD involved here, and to work with BD we should refer to the two components of BD. So we have the option to resolve this BD in this joint. We can resolve it in that joint or on this joint. Say this is point O. So this is another technique wherein if we try to resolve a certain joint into its component, let us have the most convenient point. If we try to resolve it a while ago here at point B, there we will be dealing with two force members. However, we can still manage to solve for BD, only that it is much convenient to do it here at point O. Why point O? Because BDX here as a component of BD will yield no distance at point E. Okay, that is why we will just be dealing here with the component of BD along the Y axis. Of course, we need to determine this distance. Say that is X. We can easily do that by simply referring to the slope of BD, because that is the basis for the distance of the rise and the run, or the X and Y distances. So working with that, we illustrate the truss. So here is the truss, and then this line is extended to that point, and this extended point has a slope of 1:3. So we refer to the vertical of this triangle. We know 12 feet here and 8 feet here. By the way, this is a member here. We have x 12 and 12 there. So as we can see here, one part of the vertical is 12. Okay, so one part of the vertical is 12. So therefore, it is so clear that x here should be also equal to 12. Why? Because 1 is to 3, one part and 3 parts. So we have one part as 12. What about the 3 parts of 12? That is 36. And this is already 24, and obviously this is symmetric. 12 also for the distance from point O to point A. So if you want, you'll just use bisimilar triangles. By similar triangles, we can say 1 vertical and 3 horizontal for that small triangle. This is equal to 12 vertical and x plus 12 plus 12 for this base of the triangle. So just the same, we will arrive wherein O to A or x will be equal to 12. So we're gonna place it here, 12. Moving on to the moment equation. What is the rotation of BDY? It is counterclockwise, so that should be denoted by negative. Negative BDY, and then the moment arm from E. So we are taking moments at E. So from E up to this BDY is 36. And then this 1/8 will have a positive rotation clockwise times moment arm of 24 from E, less this one, 1, 2 times moment arm of 12. All of these are equal to 0. So we arrive at BDY but not BD. But BDY can be expressed in terms of BD. We can write BDY by its slope, and the slope of the vertical is 1. So therefore, this could be written as 1 over square root of 10 of BD times 36, and all of the rest will be maintained. Therefore, BD is 2,530 pounds. And what is the orientation? So do not mind this resolving the components here, but mind where it was assumed. So it is assumed actually as compression here. Okay, so we place C as the orientation of BD. So next, we use the same figure for solving for CE. Perhaps we can delete the BD extension here. So solving for CE, of course, we obviously take moments at point B is equal to 0. So doing that, if we take moments at point B, only CE is unknown here. We have clockwise 1/8 times 12 minus CE times 8 is equal to 0. So CE would be equal to 2,700 pounds. And what will be the direction of CE? So look at where CE came from. It came from C, and CE is moving away from the joint C. Therefore, when it is moving away, this will be a tensile orientation, because you might be confused that CE is approaching E, but E here is not the point where CE was originated when it was cut by this cut section. Okay. Finally, solving for BE, we again utilize the projection at point O so that we can intersect BD and CE, because if we're going to take moments at point O here, BD will just intersect that point, so there will be no moment arm at that, and as well as CE will have no moment arm if we take moments at O. So therefore, BE will just be the unknown, and of course we have to resolve BE whether at point B. So there will be two components here, or at point E. So obviously, it is much easier to consider point E here because again, it will not involve BEX here because BEX will have no moment arm if we take moments at O. Only that BEY is involved here if we use or we resolve BE at point E. Okay, so doing that, summation moments at O, we have this negative rotation. Note that this distance is 12, so we also place 12 here, plus a clockwise 1, 2 with the distance of 24, plus BEY times 36, and all of this will be equal to 0. Okay, so we solve for BEY in terms of BE. We just write this according to its slope. So what is the slope of BE? Slope of BE is 2 vertical, 3 horizontal, and square root of 13. So we refer to y here. The slope of y is 2. Therefore, this can be written as 2 whole over square root of 13 of BE. So therefore, BE will now be the single unknown on the equation. BE here is equal to positive 361 pounds. So what is the orientation of BE here? So BE here came from B, okay? So you might tell that BE is approaching E and that you say that BE is towards this joint, but the original location of BE or the where BE is originating is at point B. So therefore, that will be the basis in our direction. So facing from B, therefore this is away from the joint. So, but we should note here that BE here should be negative from the equation, the result of equation. So that if this is negative and from your figure it is assumed to be tension, so therefore we just correct that one. We have positive 361. This is in compression because initially it was tensile and then we yielded at negative, so it is the other way around, which is compression. So this completes our problem on method of section. So I hope you have more practice and thank you for listening.